Good afternoon, everyone. Thanks for coming. This is going to be a talk about template metaprogramming. I called it a compendium, which just means I'm going to go through a lot of different techniques. And I think I have something for everybody, provided you're not a novice to C++. And I'm pretty sure that's everybody at this conference. The abstract that I wrote up describes, I think, pretty accurately what I'm going to try to do, because I'm a firm believer in examples. It's not enough for someone to tell me a technique. I'd like to see it in use. And the bulk of the examples that I've chosen are examples from the C++ standard library. I'll throw in a few others as well, but most of them will come from the standard library. And then toward the end of the second hour of this talk, I'm going to throw in something that I suspect will be new to almost everybody unless you're a committee member. It's called void T, just so that you'll recognize it when we get there. As I said earlier, this is a two-part talk. It's a single talk that has a break in the middle. That's how I hope you'll think about it. I have no particular place where I'm going to stop. It's going to get to 3 o'clock. I'll finish the slide I'm on, and I'll say, OK, let's go take a break. Come back in 15 minutes. Actually, I'll probably say, come back in 10 minutes, but I would appreciate it if we kept our 10-minute break closer to 15 than 20. Is that OK with everybody? All right, I appreciate that very much. Just one final reminder, so I don't catch anybody by surprise. I don't want to send a freshman out of the room screaming about C++. This is not for C++ novices. The assumption is you know a fair amount about the language, because we're going to dig into corners of the language pretty heavily. So let's start. I want to take just a few seconds. I don't give very many public talks, so I'll take 45 seconds and just let you know a little bit about my background. My degrees are in mathematics first, and then computer science. I actually took my doctorate in computer science from a mathematician. And what he taught me, this is a direct quote, mathematics is, after all, just a very small branch of computer science. Now, please don't repeat that to any mathematicians, but that's how he thought of it. I have had an incredibly fortunate career. I've been blessed in so many ways. I've been in academia. I did that for a decade. I actually sold hardware and ran a programming department. I've been self-employed over the years. I've lectured internationally, but not very much publicly. I did do a talk at ACCU about a decade ago, for example. And officially, I am now retired after 15 years at the Fermi National Accelerator Laboratory, where I got to do things like sit down and have breakfast with someone I had never met, and then find out he holds a Nobel Prize. Wow. That was a mind-blowing breakfast, let me tell you. I do want to point out that retired does not mean dead. So yes, I am still available for consulting work. Please call me, please email. But let's move on. Of I think more interest to this particular audience, I have been involved in the C++ Standards Committee for, well, almost 15 years now. I started in 2000. I never knew this until I was preparing this slide, and I said, gee, I wonder how many papers I really have written for the committee. And it's somewhere between 85 and 90. I hadn't realized that. And the bulk of them, it turns out, are in the last 2 years since I've been retired, which is kind of interesting. But I'm the guy responsible for putting a few things in the standard that you may already know about. cbegin, cend, that came in about a decade ago. Common type came in under the guise of Chrono. I think it came in with that paper, for which Howard was the principal author, but I contributed a little bit to that. Ratio came in pretty much at the same time, but I actually came up with that in 1998 or 99. And I'm the guy responsible for the random header. One of the talks I proposed, but they said, nah, not this time, was a talk about random. So I'd like to do that another year. I don't do very much with the core language, but I've had my fingers in a couple of features that you may recognize. Alias templates were very important to me. and I had a little bit to do with the direction that they ultimately took. There were some choices that had to be made. There was, it was supposed to go one way. I thought it was wrong. I argued and lobbied, and what we got today is the way I wanted it to work. So I'm happy about that. I did a little bit of work with contextual conversions. I first proposed variable templates under the name object templates somewhere around 2005, I think, 2004 maybe. I don't remember exactly. And then I had to drop it for a while because I was busy with other stuff. It came back in a year ago, and somebody else proposed exactly the same thing at the same time. So we ended up getting it fairly quickly at that point for C++ 14. It is not particularly well known, but there is a second C++ standard. It is the international standard for mathematical special functions in C++. So for those of you who do heavy-duty mathematics, things like Bessel functions, Neumann functions, heavy-duty mathematics, this is the standard you want to consult. And this was sort of my project from beginning to end, and I'm very proud of that, of course. And I always leave a disclaimer in my talks. I've been doing this, for almost half a century professionally, and before that, without getting paid for it. So I formed some fairly strong opinions. I'm not terribly shy about expressing them. I don't mean to offend anybody. I know the opinions aren't universally shared, but they should be. So, as I say, please be forewarned. So here's a quick preview of the examples that I'm going to try and get through in the next 2 hours. This first set, these are not in the order in which I will be showing them to you, but I've grouped these together because these are examples from the standard library. And then here's a second set of examples that aren't in the standard library, and some of them, at least, I am hoping will be in the future part of the standard library. And I put an exclamation mark next to void_t, because that's going to turn out to be a big deal. Come back for part 2. We're going to spend like 15 minutes just on void t. So let's get started. Quick introduction. What do we mean by template metaprogramming? Well, it's not just metaprogramming. Because if you look at the definition of what constitutes metaprogramming, well, I mean, this is a direct quote. It's the writing of computer programs that write or manipulate other programs or themselves as if they were data, or programs that do work at compile time that would otherwise be done at runtime. This is what Wikipedia says. Now, template metaprogramming is a version of metaprogramming that obviously makes use of templates. And the key is that template metaprogramming relies heavily on template instantiation, which of course happens at compile time, as a mechanism to do compile time evaluation. Okay? So just in case someone you're not a novice, but maybe you're not intimately familiar with what we mean by template instantiation, very quick example. If you use the name of a template in your program, not writing a template, using the name of a template, and in that context, you would normally expect to see either a type or a function or nowadays a variable. But you're naming a template instead. Then what the compiler does is manufacture, and the technical word is instantiate, manufactures the right kind of entity from the template you have named. I mean, that's a really high-level overview of what's going on. And there's a lot underneath that, but that's really what's going on. And the simplest example is the one I put on the screen. You write something like f of x, and syntactically it looks like a function call. But if f is the name of a function template, you can't call a template. You can only call a function. Where's the function? The compiler makes it for me from the template that I've named f. So that's the machinery that drives all of template metaprogramming. It doesn't matter whether you're instantiating a function template, It doesn't matter if you're instantiating nowadays a variable template, a class template, makes no difference. The machinery is instantiation. And the point of this is that template metaprogrammers exploit that machinery typically for one or both of two purposes: to improve the flexibility of the source code and or to improve runtime performance, because you're shifting work from runtime up to compile time. It's not free, it's never intended to be free, because the compiler is doing work. So you're going to pay for it in slightly, or sometimes not so slightly, longer compile times. But you recoup that at runtime because that's work that no longer has to be done. It's been done by the compiler. So a lot of people don't believe me when I say improved performance. So I deliberately went back to some talks I gave more than a decade ago, 2001. And at that time, I was experimenting with powers. So of course, everybody knows that std pows in the standard library. And then I wrote a metaprogram to calculate powers at compile time. And then I wrote a second version of the same thing. So what is it that I'm actually timing here? Well, I'm timing, and this is, I admit this is pretty crude, but I want to stress, this is 2001, okay? I measured x to the 50th power, and I repeated that 10 million times, okay? Because everybody does that every day. And these were the results I got. Now, back then, GCC was at version 2.95.2. Remember those days? Yes, okay. I turned on no optimization just to see what would happen, 0. And it was a 700 megahertz Pentium 3 running Windows 2000. How many people remember such a machine? Yeah, okay, good. Okay, so by modern standards, that's pretty crude, all right? Now, I'd like you to pay attention to the highlighted row. The numbers to look at, just for a few seconds, to keep in mind, are approximately 12 seconds, 8 seconds, and 3 seconds. Because then I turned on optimization. And back then, you didn't do 03 very often. It had issues. So I turned on 02 and kept it the same, and look what happened. The 12 seconds stayed the same, because that's the standard library, that's runtime. And my compile time from 8 seconds dropped to about 4 plus, and my runtime. And then my runtime dropped from 3 seconds to about 0.2. And for 2001, that was awfully impressive. So roughly 47% for the first version of my metaprogramming, metafunction, and about 90% improvement overall for version 2. But that's just x to the 50th, which we don't do every day. So I did one more study. And again, please keep in mind, 2001, that's why the graphics are going to be pretty crude by modern standards. So I timed std : pow, and I got this beautiful constant function, except there's these two outliers at the left. So I don't know if it's still true, but at least back then, GCC special cased 0 and 1 as exponents, right? I mean, that just screams from looking at these results. Version 1 of my pow function, metafunction, gave me those results. Almost a perfect order n curve. And then version 2, almost a perfect log curve. The point being, these aren't just pie in the sky issues. This can really, truly impact your code. And this has been true for well over a decade now. So things to keep in mind, just a couple of general things if you're going to do metaprogramming, as opposed to leave it to others to do for you. Runtime means compile time when it comes to a metaprogram. So you have to learn to do without some things that would drive freshmen crazy if you didn't let them do it. Like no variables. You can't vary anything. You have constants, effectively. Okay? So no mutability. No virtual functions. That's a runtime phenomenon. It's runtime dispatch. So no virtual. No RTTI, nothing like that. You have to do without all of that stuff. Turns out it's not really hard, but it's a mindset, which is why I mention it now up front. Okay? Some people think that template metaprogramming is hard when what they really should think about when they're getting into it is it's unfamiliar. People use the word weird. If you look it up, weird means unfamiliar. That's the right word. Everything is unfamiliar until it becomes, well, familiar, right? So to put it very simply, for the rest of the talk, no runtime. Nothing we're going to do involves runtime, okay? So let's start with the first example, just to make the point that it's not hard to shift work from compile time to runtime when you know ahead of time what the values are going to be that you put in. If you don't have the values till runtime, metaprogramming isn't going to help you. If I don't know what X is now, I have to wait and find out till runtime. But if I know it at compile time, then I can do something with it. So here's the first part of an absolute value metafunction. This is about the simplest example I could come up with. Now, there's a static assert in there for two reasons. One, if it's a 2's complement machine, you can't take the absolute value of the most negative int, right? Because there is no positive corresponding value. So that's why there's a static assert to guard against that. The second reason I put that in there is this variation on static assert is probably going to be voted into C++17 probably in November. I have a little something to do with it. Notice in C++11, you have to put in a string literal in your static assert. It becomes optional in C++17, I think. Okay? So I'm just giving you a taste of things that are in the pipeline. When there are questions, could I trouble you to use the microphone, please? Sure. Okay? My ears are older than I am, and they don't work as well as they used to.
Why?
Why what?
Getting rid of the string literal. That's...
No, I haven't gotten rid of it.
No,
it becomes optional.
Right, but why? What's the ration?
Oh, the rationale is really easy, because most of the time I don't care. Most of the time string literals, for me at least, are quote, quote. Because the diagnostic I get out of my compilers includes the text of the assert. What more do you want? I mean, that's what an assert gives you. Hey, assert fails. This is the assertion that failed. Okay, that's all I need to know. Remember, this is compile time. My customers don't see this. Right? This is intended for me and for my colleagues. So all I need to see is the text of the assert that fails. The fact that it happens at compile time, okay, so what? Okay? Anyway, that's the rationale. Now, the other thing I want to point out is the other line in the body of the struct, namely the calculation of the absolute value, which is not interesting, but what is interesting is that we end up using that resulting value to initialize. Notice there's no assignment here. Assignment is runtime. Okay? We're initializing a static const, or more often nowadays constexpr, variable. Okay? So that takes the place of what we would think of as return. This is what I mean by unfamiliar. Why would you do that? Because it works and because C++ was never designed to do this. Okay? This is what works. So what's the other side of what we've called a metafunction? Well, it's a call to the metafunction. Doesn't do you any good if you never call it, right? So how do you call a metafunction? Notice what passes for arguments to the metafunction simply become arguments to the template, because a metafunction is a template. Okay? And the call syntax is a request for the published value. In other words, we initialize that static named value. You request that value, and it looks like this. Suppose I have some const, an int, it could be constexpr. I don't care what its value is. Give it some value that you like. 42 seems to work for most people. And then you say abs of n, but n is 42, so you say abs of 42, colon, colon, value. There's your metafunction call. Okay? Now, as we'll see, over the years, people have found other ways to say this with different syntax. But this has worked ever since C++ 98. So this will work everywhere. Okay? But there's a version, a variation I will mention later that works in C++ 11. There's yet another one that also works in C++ 14. And there's one more coming down the pipeline for C++ 17. I'll mention all of those later on today. Okay? So I get asked often, what's the relationship between constexpr functions and metafunctions? And of course, constexpr functions can be very useful. If we had had constexpr functions a decade or maybe 15 years ago, I suspect half of metaprogramming today would look very different. But the main advantage of constexpr functions is that it's the familiar call syntax. You don't have that sort of awkward colon, colon value thing. You just pretend it's a real function. Well, it is a real function. It just happens to get called at compile time. So I'm all in favor of constexpr functions. But if you compare metafunctions with constexpr functions, see, a metafunction is a struct, and it just gives us more tools. Because you can make things public from inside a struct. You can't do that with a constexpr function. You can't do that with any function. You get stuff out of a function through the return and maybe via a side effect on, for example, parameters or globals, other yucky stuff, right? But when you have a struct, in particular a template in our case, you've got all these extra tools. For example, public member type declarations, public member data declarations, provided they're static and either const or constexpr, and always initialized via a constant expression. Okay? You also get public member function declarations, which are sometimes useful. Notice I said declarations, I didn't say definitions. It's actually useful. I will show you an example where having member functions declared in a struct is useful without defining the function. I'm never going to call it. I just need to refer to it. Stay tuned. And I get public member templates, I get static asserts, and you got all the tools that you can put into a struct and into a template. And most of those you don't get with a constexpr function. Nonetheless, as I say, if we were designing the standard library all over again, I think type traits would look different if we had had constexpr functions. But we have what we have. So let's take it and move on. So the first technique I'm going to mention, because it touches on several aspects, and you find this, and it's very useful. What we're going to use is compile time recursion. Yeah, why not? If it's a metafunction, you can have metafunction calls. You can have a metafunction that calls itself. Sure, why not? And the compiler has to do the right thing, and will. This works. So I picked one of the oldest known algorithms, the Euclidean algorithm for greatest common divisor, which, believe it or not, is probably in your version of the standard library behind the scenes. It gets used, I think, in some of the permutation algorithms in the standard library. But be that as it may, there's actually going to be a GCD coming down the pipe, I hope in the standard library, but certainly in a technical spec that I hope will come out next year. And yes, I have a little something to do with that. So here is the recursive part, and the call, of course, is right there. Right? I mean, that's a metafunction call. It just happens to be calling itself. So GCD is a metafunction of two, in this case, unsigned values. So I supply two unsigned values, all of which are known, and say, okay, what's your result? And whatever your result is, that's my result. But as we all know, if you're going to do things recursively, you have to have a base case somewhere, right? And how do we do that? Well, in this example, we're going to do it with a specialization. Now, I don't know how you think of specializations, but I tend to think of them as applied pattern matching. So if I make this metafunction call, I say GCD of some number comma 0, that matches this pattern in the specialization. So that's the one that's going to be used. Okay? I will refer to pattern matching a couple of times throughout my talk. And typically, I mean pick the best specialization. And, I mean, it's a simplification, but it gets you surprisingly far just to think of it that way. Okay? So, again, there's a static assert because you can't have GCD of 0, comma 0. And then if you put in some number, comma 0, some non-zero number, comma 0, you get back the number you put in. So it's sort of an identity when the second argument is 0. Okay? So I'm just trying to get you into the ideas underlying template metaprogramming if you haven't done much of it before. Okay? We're going to build on the ideas as we go. So we have a question. Yes, sir?
Just a quick question. Is there any reason why it isn't constexpr in this only
Nope.
const?
Nope.
No, it just...
The reason was I wrote this from a talk I gave a couple of years ago before we had constexpr.
Okay, thank you.
If I were doing it today, I probably would do constexpr. But the point is, this will work with older compilers. And if that's important in your context, have at it. Const works just fine. Okay? Let's move on. One of the really interesting things about metafunctions that you cannot do with a constexpr function, cannot do it, is you can write a metafunction that takes a type, not a value, a type as its argument, or a parameter, depending on how you want to look at it. Now, we have a good example in the language. It's been there for a very, very long time. It's named size of. If you think about it, size of whatever, the whatever is allowed to be a type, not a value, a type. So we have precedent for metafunctions that operate on types. The difference is we can now write our own using template metaprogramming. So here's a simple example out of the standard library. There's a metafunction named rank. It's in type traits. Most of my examples come out of type traits. So there's a metafunction named rank, and like most of these, it's going to be in two parts. So part 1, this handles the case that the type I give you is not an array. If it's not an array, the rank is 0. Period, end of story. And I've highlighted this place where that happens. Okay? So if this is chosen, the metafunction will return, if you will, 0. Because a scalar has rank 0. On the other hand, if the type that you hand me is an array type, and you can see that it's an array type because the specialization is on a type brackets n, that's an array type. Actually, it's a bounded array type. Then the rank is at least 1 plus, recursion, the rank of the rest of the type. So for example, if your type, which I've named here array underscore t, if your type is int sized 10 by 20 by 30, that's going to have rank 3. And this all happens at compile time. This all happens at compile time. Okay? So this is just a little bit of a twist on my previous example in two ways. One, it illustrates that you can have type functions, type metafunctions. And second, it illustrates that that the recursion doesn't have to be in the primary template. You can put the recursion in the specialization if you want. Nothing wrong with that. Okay? Let's move on. Better yet, a metafunction can give you a type result. The previous example took a type but gave you a number. Turns out most of the metafunctions that are type functions that I write take a type or take several types and give me back a type. So as our example, let's take remove const. Now, compile time, nothing gets removed, right? Nothing can change. There's no mutability here. So what it really says is give me back the same type, except if there was a top-level const, ignore it. Give me back the rest of it. So it's written like this. A primary template that says you give me a type, I give you back the same type by default. If you didn't have const in it, you're fine to, to start with. Otherwise, the specialization says if you handed me a type with a top-level const in it, I will hand you back as a result the same type minus the const. Right? You hand me u const, I hand you u. That may be bad English grammar or physically impossible, but programmatically it works. Okay? So one of the real bonuses of template metaprogramming are type functions. The calling sequence for type functions is that instead of asking for : value, you ask for : type. And it turns out, starting in C++ 14, and I had a little something to do with it, there's also a way that you can just say _t and avoid having to say : type. I'll mention that again a little bit later on. Okay? That's C++ 14. And for things in the standard library, you don't get this for free with your own metafunctions, but it's not hard to make this work. It's just an alias. So I've already used these, but I want to highlight the fact that over the years we have developed two conventions for metafunctions. And I urge you to obey the conventions, just because it makes things easier to read. Okay? Otherwise, you're in the situation of having to learn several different ways to spell the word return. You would never want to do that. So I urge you to follow the conventions if you write your own metafunctions. The first convention is for metafunctions that have a type result. Okay? And the convention, as you've seen, is that whatever you point out as your result, you alias it by the name of type. And I'll point out right away that standard library is not entirely consistent, but it's for historical reasons. There are metafunctions that just predate type traits, for example. Okay? And iterator traits is my favorite example to pick on. It is the damnedest metafunction I've ever seen, now that I think about it, right? Because number one, it doesn't have a result. It has 5 results. It has things like reference, and it has things like iterator tag, and it has 5 results, and none of them is named type. One is named value type. Thank you. It gets close. Okay? But that long predates what we have learned about metaprogramming. Okay? So the standard library is not 100% consistent, but all the modern stuff really is. And my favorite example is the identity metafunction. You've actually already seen this as a part of remove const. Be with you in 1 second. But I find it useful to have an identity metafunction, and I'll show you why in just a second. So I've chosen to name it type is. The standard library at one point temporarily had something named identity. I say temporarily, it was in a working draft for a couple of drafts, I think, and it got ripped out. It turns out the name is contentious because some vendors have already supplied something named identity and they didn't want to have to change it, and so on and so on. So I name mine type is. And it's just a straight identity metafunction. You hand me a type, I hand it back to you. Turns out to be surprisingly useful. Simple things usually are. And the way I use it is as inheritance. So let's look at remove volatile, which of course is a simple variation on remove const that I showed you earlier, right? So you hand me a type t, and by default, namely if it doesn't have a top-level volatile, I hand you back the same type. I say type is t, and I inherit from that, and I get my member name type. And now I can't risk misspelling type I can't risk forgetting to do it. I just say the type is T. On the other hand, if you hand me a type that is volatile qualified, then the type is U. Okay? So let me please take your question.
Sure. Going back to the iterator traits example, so would you say that in general it's an anti-pattern to have a traits class with multiple members?
I would, well, is it a traits class, or is it 5 metafunctions bundled together? For me, it's the same question as, do you have a function to calculate a mathematical sine and a separate one for mathematical cosine, or do you write one function that just hands you both? Do you do division and remainder in one function, or are they separate functions? Because you're doing the same work. You're just saying, give me this half of the result or give me that half of the result. And one way to get performance, as we all know, is to put things together under a bigger dust cover. Right? So you bundle things together, and sometimes you can improve performance. And you get other perceived benefits, but you also lose. So I'm sorry, it's an engineering question.
Okay.
And that just means there are trade-offs.
That's good enough.
Okay, thank you. Nice question, appreciate it. All right, let me go forward again. All right, so I'm heading into something different now. Still, it's all metafunctions, so it's the same, but this is a little twist. So first, just imagine with me, and some of you who are pretty advanced will know where I'm going, but bear with me if you would. Imagine, let's just do some pie-in-the-sky designing. Imagine a metafunction if with an alias if underscore t to do the call. And what it does is it lets you make a compile time decision between 2 given types. I want either this first type or else I want this second type, which is why I picked the name if, right? And I want that based on a predicate, of course, the result of which I know at compile time. Now, before we go off and look at the details, which we will, what good is this? Well, hold on. If you haven't seen this before, just hold your horses. Look. You can write self-configuring code. And just to make a tiny example, suppose I've got some, looks like a variable, but it's const, of course. Let's name it Q just for simplicity. I don't have a lot of real estate to work with here. So Q is some int value. Suppose I care whether or not it's negative. Just suppose, okay? So if it's negative, I want to declare my variable k as an int. Otherwise, I want to declare my variable k as an unsigned. Happens automatically just by setting Q before you run the compiler. Or I have 2 other function objects named capital F and capital G. I want to instantiate and call either the one or else the other. Happens automatically at compile time. The decision is made by the compiler based on the known value of Q. Or, one last example. I want to inherit from one of 2 possible base classes. If Q is negative, inherit from B1, otherwise inherit from B2. Just a tiny taste, and this all happens at compile time. All you have to do is adjust Q. Okay? At compile time, before you run the compiler. All right? So, how do you do this? Well, let's implement if. It is so simple. It is astonishingly simple. Again, a template, a primary template, and then a specialization. So the primary template, you get to choose when you implement it, but I've made the choice here. Let's assume that the primary template handles the case when the bool is true. Right? It's as good an assumption as any. Assume it's true, in which case the result, type is T. You hand me a bool, you hand me 2 types. I don't even have to name anything but T, because I never refer to it. And there's a pretty standard rule. If you never refer to it, why does it need a name? Yeah, you can have declarations that don't name anything, right? You can have anonymous variables. You don't have to name every type. All right? Struct, open brace, stuff, 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 close brace, variable name. Never name the struct. You don't have to name things if you don't have to refer to it. If you want to refer to it, you have to name it. Right? So, by default, type is T. See why I love type is? I could just read this. I could read this to somebody over the phone and they'll get it. The specialization handles the case of false. You hand me false, you hand me T, you hand me F, two different types, and the type result is F. Done, done, done. That's all there is. Incredibly simple once you've seen it. Okay? It turns out we actually have this in the standard library since C++11, but I wasn't in the room, and so they ended up naming it conditional. So, you know, my spell checker has more work to do. It turns out we did a little bit of augmentation of the standard type traits in C++14. I referred to this a little bit earlier. I had a little bit to do with this. And now we have as well conditional T. This is C++14 and onward, conditional T, so you don't, as I say, you don't have to say : T. And this is true for all the standard library type returning metafunctions. Okay? They all have the _T convenience call, I think I called it. So let's take a variation on conditional. And this blows people's minds the first time they see it. Because I know I saw this a decade ago when Jaakko Järvi showed it to me. And I looked at it and said, what are you doing? You can't do this anywhere else in C++. You can't refuse to have an answer. Right? I mean, you can bring your program to a screeching halt. You can call std terminate if you really want to. But other than that, if you have a function, you expect it always to return something. You can't say, I got nothing to return to you. Go away. Okay? Yeah, you can throw exceptions and stuff like that. But in normal code, you can't do this. So here's what I want, and I'll tell you why in just a second. I'm going to hand you a bool and a type. If the bool value is true, give me back the same type. Otherwise, give me nothing. Literally. So first, how do you do this? Trivial. Okay? It's called enable if. It's in the standard library. You give me a bool, you give me a type, and by the way, the standard library defaults that type to void. That's not essential. It turns out to be useful. So you don't have to even give me a type if what you want is void. Okay? But fundamentally, you give me a bool, you give me a type. If your bool is true, I'll give you back the same type. Otherwise, I give you nothing. Empty braces. I give you nothing. Okay, fine. So what good is this? What good is it to have a function, any kind of function, let alone a metafunction, that refuses to give you an answer? Well, hang on. Look at this call. Enable if, where the bool is false, but I'm referring to : type anyway, but as we've seen, there is no type member. Oops, that's an error, right? No, it's sometimes an error, and welcome to SFINAE. And if you haven't seen this before, SFINAE, the name was coined, I think, by David van der Voorde, I think now over a decade ago. Formally, this is explicit overload set management. I've never heard anybody refer to it that way. Everybody always says SFINAE. Substitution failure is not an error. So let me explain what that really means. This is not metaprogramming per se, but it's something that you can use profitably in your metaprogramming. Okay? So it goes like this. First, you have to understand when it happens. It happens during template instantiation. Right? So you're instantiating a template, which means there's some metafunction call, which is the reason why it's being instantiated. Okay? So what happens in instantiation? And of course, I'm simplifying. No question about it. There are lots of details under the cover. But fundamentally, a big first step is figure out what are the template arguments that we're going to use to instantiate. And fundamentally, template arguments can come from any of 3 different places. And I'm sorry, they can come from all 3 in the same metafunction call. Okay? If client code supplies the template argument, we take it verbatim. This is what you wanted. This is what I'm going to use. If you don't, and if it's a function template, then we can deduce the template arguments, usually or often, from your ordinary function arguments. We can look at the types and so forth. And if none of that works, then I can look at the default values in the declaration of the template. And you can do all 3 in the same instantiation. Okay? But an early step in instantiation, and you know, I don't know the details of every compiler in the world, but this has to be done. Otherwise, the compiler doesn't know what to instantiate. So now I know this, let's instantiate. So what I do is I have to use those arguments and use those as replacements for the placeholders, which were the parameters, right? So we're doing substitution. Okay. Now there are 2 possibilities. Possibility 1 is all goes well. We want this to happen, usually. So if this gives you well-formed code, all is fine and the instantiation succeeds. But if the resulting code is not well-formed, and of course the term is ill-formed, if you get ill-formed code, doesn't matter how or why it's ill-formed. If it's ill-formed code, then the compiler will say, well, that's not viable because substitution has failed. There's the SF in SFINAE, substitution failure. And that instantiation that never was is silently discarded. It's not considered an error. And there's the rest of SFINAE. Okay? It's not considered an error. And we can make profitable use of this. And I'm going to show you some examples. Question first.
What you're saying here is only true for function templates, right?
No.
I mean, the last line at least. You don't discard class templates.
Well,
Yeah.
Yeah. Metafunctions are class templates. So
But
I admit there's a gray area there, but
you said the overload is
for-
discarded, right?
no, I didn't say anything about overload. I just said if the resulting code is ill-formed. It is most commonly used, SFINAE is most commonly applied in the context of function overloading, yes, but not exclusively, okay? But that's where it gets that alternate name of overload set resolution or overload set management, okay? All right, so let's put this into use. And I'm just going to give you some made-up examples here, because the real ones tend to be a little bit too big. We're going to make use of it a little later as well. Suppose that what I want is 2 versions of an algorithm F. And I want one version that deals very well with types that are integral and nothing else, and I have a separate version that deals with floating point types. Okay, no problem. So I want at most one of the 2 to be instantiated. Because you hand me a type, it can't be both integral and floating point. Those are 2 different kinds of types, right? So at most one is instantiated. And so I say, enable if t of is integral of t : value. So what this, notice syntactically, I've put this where a function expects to put a return type. Right? Syntactically, I'm declaring a return type. Whatever enable if returns is the return type of the function. Okay? So if this is chosen, my return type is going to be maxint_t. On the other hand, if t is a floating point type, and the reason that this works is at most one of these is viable. The other one is not viable because enable if will find the query to be false, and there is no type. And it has nothing to return. So I say : type, but there is no type. So that's ill-formed. It gets discarded. It never makes it into the overload set. So at most, one of these gets instantiated. And what if neither type trait says true? Suppose I call f with, for example, a stood string. Well, both those metafunctions will be ill-formed, silently discarded. Neither one is viable. You're going to get an error from your compiler. Hey, I don't know. There's no function f that matches. And that's exactly what you want. Okay? So there's SFINAE in a nutshell. Yeah, there are more things you can do with it. Yes, there are more details to be learned. But it turns out to be incredibly useful. And this just goes into your toolkit. Those of you who listened to Bjarne today heard him talk a fair amount about concepts. Some of you attended Andrew Sutton's talks yesterday afternoon. He talked about concepts, of course. Just in case you missed either or both of them, I'll give you a quick taste of concepts as it relates to enable if that we just looked at. Okay? I am as optimistic as Bjarne. I've been waiting for concepts for a very long time. I did a little bit of work on the C++11 versions of concepts that ultimately got yanked. So I care about this a great deal. But I do want you to know that concepts has a very solid mathematical foundation. And that means it is a solid, well-baked idea. Not only has Alexander Stepanov been working on this for several decades, but long before him, there was a wonderful mathematician by the name of Emmy Noether, and nobody's ever heard of her because she lived in an era when women couldn't get faculty jobs. So somebody else who was on the faculty hired her to deliver his lectures for him. I'm doing this from memory, but I think University of Berlin. She is now recognized as the true originator of that branch of mathematics that we now call abstract algebra. Some people refer to it as modern algebra. Groups, rings, fields, ideals, that kind of stuff. Concepts, if you look at it deeply, it hooks into all of that. So there's a lot of mathematical underpinning going on. That should give you a fair amount of confidence in it. But I want to do a really, really fast comparison of today and maybe next year. So here is half of my previous example, just verbatim. Enable if is integral. With concepts, it might look like that. And I don't have to do the enable if dance, and I don't have to rely on SFINAE because the compiler will do all that stuff for me without my saying much more. Okay? So I just want to show you those side by side. Now, I said there is a second convention. Again, you've seen it because I've used it in my earlier examples. The second convention is for metafunctions that return values. This is where a decade or more ago we might have put in constexpr functions if we had them, but we didn't. And we're not going to change it now because stability is very important to us on the committee. So the convention is if you're going to have a value result, you name it value. And when you want to do the metafunction call, the client says blah, 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 : value. Okay? There are also some additional things that we have put into the standard library. So the canonical value returning metafunction that you hardly ever use directly unless you are doing metaprogramming. So this is a tool for metaprogrammers for the most part. Okay? It's named integral constant. Okay? And the part that you really care about is the fact that it has a data member named value, static data member named value. Okay? But it also has some other stuff in it to make it more convenient to use. And the way that you use integral constant is that you inherit from it. Just like I did the inheritance from my type is, you do the same thing for value returning metafunctions, but you inherit from integral constant. Okay? And I have examples. So let's redo rank. It's the same metafunction we looked at as an example earlier, but let's use the convention the way the standard library would. So the primary template, as before, handles non-array types. The rank is 0, so you say integral constant, type is going to be size t, and the value is going to be 0. Okay, done. Part 2, a partial specialization that handles bounded arrays. And you inherit from integral constant, size t, of 1 plus rank of the rest of it. Okay? So this is very similar to what you've already seen. It just obeys the convention that we've adopted. And by the way, the previous version wasn't complete. So let me do this one completely. There is a type called an unbounded array. So it has a rank too, but it's a different pattern. So it needs its own specialization. Okay? All right. So I think it must be around 3 o'clock now. 4 minutes to go. Shall I do one more slide, or do you want to go get something to drink? One more? Sure. One more slide. So here are some things that I have done that I find useful, and then what the standard library has done. I just made something, an alias. You can see it in its entirety right there, because I return a lot of trues and falses from metafunctions, right? So instead of my having to type integral constant of bool every time, I just say bool constant. And then, for example, true type is a bool constant whose value is true, and false type is, well, guess what, right? That's just the way I have defined it for myself. I have my private version of the standard library. This is what I chose to do there. I just find it convenient, okay? I hate to type. I really hate to type. It slows me down, all right? Now, I also want to point out, I referred to this a little bit earlier, but metafunction call syntax has evolved as we've learned more about it. So the original version still works. If you have a metafunction, my example here is void, and we're going to return to that later on a couple of times. But if I have a metafunction named isVoid, I can ask for its value today in up to 3 different ways, and tomorrow 4 different ways. So the one that's always worked is : value. That's the only one I've used so far. In C++11, Alistair Meredith, I think, was responsible for this. He added the cast member function to integral constant, operator t. So now you can ask for the value implicitly. You can say, well, give me the result cast to bool, and the cast will just happen implicitly. And then in C++14, we actually have an operator parens in integral constant. Sorry, I had something to do with that. So you can now take your metafunction, instantiate it. You have to instantiate it. And I use braces for that. And then call it parent, open, close parens, and you get the result. You could do open, close parens, and the first one instantiates and the second one calls, but I just look at that and it boggles me. So I don't do that. I love open, close brace. And then the final version that I had thought of for C++14, but decided it was too drastic, and then Stefan, who's sitting right there, came along and said, nah, we should do this anyway. But we, didn't happen in time for C++14, but I think it's ready for vote in November, if I remember correctly. Just like we have the _t for type results for metafunctions, we're going to have _v for value returning metafunctions in the standard library. And of course, we can only do that now because we have template variables. Sorry, variable templates, okay, which is a new C++14 feature. We should have had it a decade ago, but I didn't push it hard enough at the time, okay? So now I think we're at a good place to stop. Let's everybody go get something to drink. Please be back in 10 minutes, right? Closer to 15 than 20. See you then. Thanks very much. Thank you. Thank you. Thank you.